start of the recording. Okay, and back to my, we'll go to my OneNote. Go back to my OneNote. Come on, OneNote. There we go. Okay, you know what I will do is I'll share this with everybody, the class notes. Actually, I'll wait and I'll share it once I've filled it in, if you prefer, so that you can go into your own OneNote and look for it. I'll probably be going a little fast for you to draw all of this stuff, but feel free to just make sketches if you're making notes. I noticed some of you aren't big on taking notes, which, I mean, it's your nickel. You can, if you don't want to take notes, you don't have to. But pay close attention. I'm going to go kind of quick on this one because I'm going to cram 5.1 and 5.2 together. On the plus side, pretty much everything I've talked about is just building on things you should already know. Like, for example, you saw in grade 11 what 1 over x squared looks like. They call it, the nickname's the volcano. I always call it the Atari. Kind of reminds me of the Atari logo. And does every graph that has a 1 over x squared look like that? See, that's the thing. All parabolas have the same shape, basically, right? They can be wider or skinnier, but they're all basically the same shape. Every linear equation, of course, linear means linear, straight line. But does every 1 over x squared look like that? No. Do you remember there's 3 basic shapes? We call that one the volcano. The other 2 shapes were the driveway and the speed bump. Do you remember that from grade 11? It was one of the things you did towards the end of the course. Well, I think we're going to see all 3 of those today. And then, of course, what happens when there's an x on top as well is just a 1 or a constant on top. Well, to quote Dr. Evil, and then it gets weird. So first thing we have to do is remember that there's a definition you learned, again, in grade 11. I'll even jot it down. I'll just move over and jot it down. Oops, come on, black pen. The asymptote definition, my grade 11 definition, if you like, was, well, let's say a vertical asymptote. The vertical asymptote's grade 11 definition was values that x could not equal, right? And then, of course, you'd make a dotted vertical line, and of course, your function can approach but not touch that line. The asymptote. And that was a perfectly serviceable definition in grade 11. Perfectly fine. It's even pretty good now. But, okay, you guys are writing a big physics test. Think about the way physics works. If all you care about is things like temperature and what state a matters in, then the model of particles and atoms are just little billiard balls is perfectly fine. But once you start getting into chemical properties, once you start getting into the way chemicals actually bond and interact with each other and react with each other, that definition breaks down, right? It's not nearly sophisticated enough because you have to start thinking about the particles that make those little things that behave like billiard balls. And then, of course, once you start studying light behavior, they don't behave like billiard balls at all. I can't throw a billiard ball out the window and the door at the same time, but boy, I can do that with a photon. So, for example, here in intro calc, we have to kind of come up with a more, what's the word? Maybe a more sophisticated definition of an asymptote. And notice this word here, approach. That remind you of anything? Guess what we're getting back into? Begins with an L. Limits, yeah. So we're going to take like a limits definition now. Here is just a little table of values for 1 over x squared. And as you can see, the bigger x is, or the more negative it is, I'll start using the terminology big negative. I know that that's kind of that's a poor choice of English in a way, because really negative 1 billion is smaller than -2, technically, right? When it comes to what's greater than, what's less than. But when I want to say a big negative, I mean way out there on the left side of the number line, okay? Can we all agree that that's what I mean? Okay, cool. So, doesn't matter how big a negative is, this thing's just going to get smaller forever. That's, of course, not what I'm worried about. I'm worried about the vertical asymptote, first of all. So what's the vertical asymptote of this thing? Well, the closer I get to the y-axis on either side, the bigger the number is, right? How come on either side? Well, because I'm squaring it. So it doesn't really matter whether you're approaching it on the left or the right. You're just getting bigger forever. So you would, of course, say that the limit as x approaches infinity for 1 over x squared, or sorry, that's not what I meant to say, as x approaches 0 is, of course, going to be infinity, right? And you can kind of see that in the graph. The closer you get to x is 0, the higher this thing goes, right? So if that makes sense to you, move those little squiggles. Basically, for any function f of x, if any of these is true, if as you approach some value a from the left, remember that means approach from the left, the negative after the a. It's like, oh great, what do we do in chemistry? What's with the little negative after the number up in the top? No, that means from the left, right? And as x approaches a positive, which means approaches a from the right. And of course, remember if I just say as x approaches a, I mean from either side. Remember, the limit doesn't exist unless both of those sides are the same number when you approach from both directions, right? Remember that? Reviewing limits. Okay, so if you approach a from the left, you approach a from the right, and you're infinity, or if you approach a from the left and a from the right, and you're negative infinity, if any of those things is true, then you can say that f of a, or sorry, that's not what I meant to say. You can say that x equals a is a vertical asymptote. And that's basically how you define a vertical asymptote in calculus, right? It still kind of means the things x can't be. But it can't be them because what's happening? Well, because as you get closer to it, you either shoot off to positive infinity or you shoot off to negative infinity. It's not just a number you can't touch. Because remember, there are other types of numbers that you can't touch. There's just basic discontinuities. Remember that? Where you just have a little hole in your line. This is different than a hole, right? It's a line you can't touch, but the closer you get to it, the more you head to positive or negative infinity. And so let's do a very simple example. This is as simple as it gets. 1 over x, right? So what happens when you approach 1 over x from, say, the right-hand side? So the limit as x approaches 0 of 1 over x from the right-hand side, well, you can even just kind of reason this out, like make a little table of values in your head, like the one you just saw for the last example. The bigger x gets, the smaller it gets, but it's still positive, right? So the smaller x gets, the more and more it goes bigger, right? If you put in a tenth, you get 10. If you put in a billionth, you get a billion. So you are heading towards positive infinity. But if you take the limit from the other side, right? Again, put in negative a tenth, you get negative 10. Put in negative a billionth, you get negative a billion. You're heading towards negative infinity. It's kind of interesting to think about the fact that the closer these two limits get to each other in terms of the x values you're putting in, the farther apart their y values get, right? Which is a strange idea until you kind of look at the graph and go, oh yeah, that is exactly what happens. Because 1 over x graphs all look like that, right? Okay, it's a good example too. Now, that is a 1 over x squared graph, right? Remember that the one we just saw, 1 over x squared with no bells or whistles, was this guy. So what changed about it there, using those of you who've done the grade 12 function graphing unit? What did this 2 do to it? Shifted it 2 up. What did this minus 6 do to it? 6 to the right, so that shifts my vertical asymptote over, which is what we're about to talk about. And what does this 5 do to it? That would be a vertical stretch, right? So think about what that's going to mean for this function. So you kind of maybe already have a basic, oh, and one other thing, what does this negative do to it here? It's going to flip it over, reflect it in the x-axis. So hopefully now in your head you already have a picture. Your grade 12 skills give you a good picture. But let's talk about its asymptotes. So if x gets close to 6, of course, in this function, I should probably put x cannot equal 6, right? Why can't x be 6? Because you can't divide by 0. So if x gets close to 6 on either side, in other words, because I'm squaring this thing, right? If I put in a number very, very close to 6 but a little bigger, I get a decimal that's positive that gets squared. So it gets to be an even smaller decimal. If I put in a number really close to 6 but smaller, like 5.99999, I'll get a negative in the bracket, but when I square it, it becomes positive anyway, so it's the same thing, right? So if x gets close to 6 on either side, you would get a very small positive number, and you're minusing that from 2, so therefore, I would say the limit as x approaches the value I can't have, which is 6, of this function, is going to be negative infinity, right? Because of this negative. So that tells me what this thing's going to do. So I can actually kind of say, all right, there is an asymptote. It's a vertical asymptote for this function at x equals 6. So let's see. Let's go back. This is cool. I never realized I could do this till now. There we go. So there's 1 over x squared again. And again, what's this going to do? What's going to change about it? Well, that asymptote that was here. Can I draw on this? Oh, no, I'm not going to be able to draw on it. I thought I could draw on it. Go back to home. The asymptote that is here, what if I highlight? No, it doesn't let me do that either. Okay, I'll figure out how to do that later. What if I click off of it and then onto it? No. I could have swore there was a way I could draw on it. Anyway, y equals 0, x equals 0, the y-axis is an asymptote. It gets moved over 6, it gets reflected in the x-axis, the 5 stretches it out, and the 2 shifts it down. Or sorry, shifts it up. So boom. There we go. There's my new graph. And again, I have x equals 6 as an asymptote. All right? So that's example 2. And that's our good quick introduction to, or review, I should say, of vertical asymptotes. Let's talk about horizontal asymptotes. Again, in grade 11, my grade 11 definition is just my function can't touch, and I'm going to put this one in quotes, y equals some value, being that because y can't be that value. And in grade 11, we made sure that we never threw functions at you where that wasn't true. This is where things get a little different. This is where we have to adapt our thinking a little. This is very definitely a definition that doesn't work anymore. Because unlike a vertical asymptote, which is untouchable, why? Because you can't divide by 0. Horizontal asymptotes are crossable and touchable in some parts of the function and not others. For example, check out this guy here. F of x equals x squared plus 2 over x squared plus 1. Now, I remember last year I used this example and had somebody, I asked, well, what do you think this shape is? And I had some people say, well, maybe it's linear because you have x squared over x squared, so don't those cancel and you just get a straight line like a constant? The answer is no, it doesn't really cancel. And if we had more time, I would actually ask you to do something with this that might help you kind of picture what its shape is. You could long divide it, right? We did learn how to long divide functions. And there'd be a remainder, right? In fact, you can kind of see it would be 1 plus some sort of remainder. And how do you write remainders? You can write them as fractions. So you get some sort of number over x squared plus 1. So it is an x squared graph. So then I had people go, oh, okay, so it's either a volcano, or it's a driveway, or it's a speed bump, which is, again, the 3 shapes you learned for 1 over x squared graphs in grade 11. Well, it's a little more complicated than that even. First of all, does this thing have vertical asymptotes? Because certainly the driveway graph has vertical asymptotes. The Atari graph or the volcano graph has a vertical asymptote. The speed bump doesn't, so maybe it's a speed bump. What do you think? People are shaking their heads no, there's no vertical asymptote. How do you know that? How do we know just looking at it that there's no vertical asymptotes? Guys at home, you can play too. How do we know? What do you got? Perfect. There's no number here where the denominator would be 0, right? Try it. How do you make x squared equal to -1? You'd need to use I, right? Because you'd have to square the square root of -1. So there's, in real numbers, there is no way to make that denominator 0. So I don't have any vertical asymptotes. No vertical asymptotes. But, again, my grade 11 definition of this would be, well, are there numbers y can't be? Just pop back for a sec. I didn't bother talking about it here, but there is a vertical asymptote here. There's a horizontal asymptote on this guy. And it is, of course, you can see it in the graph here. It looks like it's 2. Why is it 2? Because there's no way to make this thing 0. So if that thing can't be 0, think about it. 5 divided by anything can't ever be 0. So if this thing can't be 0, then how would I ever get y to be 2? Get it? That's why it's a horizontal asymptote. And that's, again, the way you would explain it to a grade 11 student. And that's fine and dandy. But notice in this example, that's kind of hard to do, right? What is it? Because once again, there are values that would make x plus 2 equal to 0. Or is there? Well, wait a minute. No, there isn't. Not in real numbers. So how do we approach this? Well, let's look at a table of values. As I get bigger for x, look what's happening to the numbers. I go from 2 to 1.5 to 1.2 to 1.1 to 1.0 and change to 1.0 and less change, and less and less and less. What's the trend here? It looks like as x gets bigger, y is approaching 1. Now, is that a number that y can't be? I don't know. Is it a number y can never touch? Well, let's see. But certainly, here's the definition that we're going to use for a horizontal asymptote now. The line y equals L is called a horizontal asymptote of some curve if either the limit as x approaches infinity is a line, f of x equals L, or as I head to negative infinity, it's L. Notice it doesn't say there's anything that the y value can't be, right? That was a nice primitive definition that worked for us in grade 11, but the functions we're going to look at now are too complicated for that. So that's our new definition of a horizontal asymptote. And let's take a look at that function before we move on to some others. Y equals x squared plus 2 over x squared plus 1. And I have it on this graph here. Let's see if I can bring that up. So go back to home and turn on, where did I put it? I have it here, right? There we go. And yep, people who guessed it was a speed bump because there was no asymptote, you were right. Nice job. But notice it does have a number that y isn't going to be. It looks like the value is y equals 1. So how do we come up with that? So go back. So it looks like there's a line that this thing can't touch. And it's the line y equals 1 is a is a horizontal asymptote. Now, without having to, do a table of values and draw the graph, how could I have found that? Do you remember doing these? Remember limits to infinity? So who remembers the algebraic trick? There it is. I am going to use my property of 1. Remember that? You can do anything you want to an expression if it only involves multiplying or dividing it by 1, because that's the one thing you can do to anything that doesn't change its value. So I'm going to multiply by 1 over x squared to both the top and the bottom. Or if you like thinking about it as I divide top and bottom by x squared, and then I'm finding the limit as x approaches infinity of 1 plus 2 over x squared and 1 plus 1 over x squared. If there's anybody here who's watching this going, what the heck is he doing? You're going to have to go back and review the limits unit, right? So that's going to be now that I won't be putting infinity into, now that I won't be dividing by 0, if I put infinity into the equation, I can say that this is 1 plus 0, or yeah, because 2 over infinity is basically nothing, right? And 1 plus 0, and there it is, 1. Therefore, f of x equals 1 is a horizontal asymptote. Okay. Now, like I said, even this thing, speed bump, is a pretty simple curve, relatively speaking. Right? Again, you saw them in grade 11. Curves get weirder. Look at this guy. This is I believe this would be some sort of a variation on the speed bump where I actually had x squared on the bottom and some sort of x squared on top that also had another x value, like an x squared plus x. But it goes down at the end, so actually that means maybe it might be cubic as well. And as you can see, it crosses that horizontal asymptote there. But then, as x approaches infinity, the further I go that way, I won't cross it again. So it's really, if I'm sticking to that grade 11 sort of definition, a horizontal asymptote is something that the function can't touch as I head in one direction, but that doesn't mean I can't cross it in the other. But our definition now is, well, it just turns out that as I approach infinity, this is the line that it keeps getting closer and closer and closer to. Right? So you can cross horizontal asymptotes or not cross horizontal asymptotes like that one. Or, here's this one. Anybody take a guess as to what kind of a monster this third one might be? I'm over here now. Look at the going up, going down, going up, going down. What kinds of functions did you see in grade 12 do that? Sine curves. This is some sort of trig function. But why is it getting smaller and smaller and smaller? Well, because there's some other type of function that it's multiplied by or divided by. Like, for example, something along the lines of a sine of x divided by x, right? When x is 1, hey, no problem. That's the sine of 1 divided by 1. But when x gets bigger and bigger and bigger, the whole fraction gets smaller and smaller and smaller. But it's going to not kind of keep pace with the numerator. See, the numerator, the sine, you can put in sine of a billion. You're still going to get a number somewhere between 0 and 1, right? So all the numbers on top are between 0 and 1. But all the numbers on the bottom get smaller and smaller and smaller forever. Or sorry, bigger and bigger forever. So the whole function gets smaller and smaller forever. So that's what kind of I have a feeling that thing is. It's something like that. And as you can see, what's happening is it's getting closer and closer and closer. It's approaching the line L. Okay? All right, so all of these guys, they're all approaching some line L. This guy has 2. It's approaching line L on the top and line M on the bottom. Can you have more than one horizontal asymptote? Yep, just like you could have more than one vertical asymptote. All right, let's try another one. Let's evaluate that guy. So same trick, the limit as, the limit as x approaches infinity And what I'm going to do with this thing is I'm going to divide everybody by x squared, or again, I'm timesing top and bottom by 1 over x squared. And we haven't done this in a while. Months ago we did that unit. Okay, so that's going to be the limit as x approaches infinity of, okay, so this guy's just going to be a 4, right? This guy's going to be minus 1 over x. This guy's going to be, this one doesn't simplify, 2 over x squared. This one's just going to be a 6 because those x squareds cancel, plus 5 over x plus 1 over x squared. Now, as x gets infinitely big, these things here just get closer and closer to 0, right? So if they get closer and closer to 0, I can just say that this is 4 over 6, which is 2/3. So I am expecting the graph of this thing to approach the line keep using "and" when I mean to say "ah," is a horizontal asymptote. Let's see. Let's have a look. I don't have that one queued up. I'm going to have to go over Desmos. Desmos. Come on, Desmos. There we go. And there it is. And as you can see, let me move that in. That one's kind of the driveway graph, only the part that's in the middle kind of shoots up. And the two kind of curbs, oh, actually, I can't touch that without moving it. Go back. The two kind of corners here at -2 and down here, they're not symmetrical anymore. I told you, when you start putting x's on top of graphs where there's x squared in the bottom, they get strange. So this guy here, and this has an x squared on top. So this guy here does have that sort of kind of driveway-ish shape. But look what happens here. Follow my okay, what is 2/3 again? 0.6 repeating, right? Notice what happens is as I get closer to infinity here. Let's see, can you see the dots there? Well, here we go. Somewhere around here I cross 0.6 repeating. But then after I round that corner, I'm going to get closer and closer and closer to it, but it becomes an asymptote from there on. So if I actually graph, here I'll actually graph it. If I graph y equals 2/3, and close that. I don't know why it's happening. Oh, for some reason it capitalized y. Oh, you stupid keypad thing. Y, there we go. That's what I wanted. There we go. So we definitely cross the horizontal asymptote when we're close to the y and the x-axis. But heading to infinity this way, nope. It's going to become an asymptote. And heading towards infinity this way, it's going to be an asymptote. And I can prove that too. Let's go back to the actual question again. What were to happen if I was doing the limit as x approached negative infinity? Would it be any different than that? Not really, because dividing 1 and 2 and 5 and 1 by negative teeny tiny decimal still isn't going to change the fact that that's 4 over 6. Right? So as you can see, you get the asymptote from both directions. Okay, cool. Couple more. If I run out of time, I'm going to keep going. Those of you who have to run off the music, you can just watch the last few minutes of the video, because I think I got like a couple more examples that I got to finish here. Okay, so find the horizontal and vertical asymptotes of this function. So this time we want to do them both. So let's find the vertical asymptotes first. So how do I find the vertical asymptotes? I have to figure out, is there a number that we can approach here? So let's see, what are my horizontal and vertical asymptotes of that thing? So let's see. Well, let's do the horizontal ones first, actually. So my horizontal asymptotes are, take this thing and divide it by x on the top, and x on the bottom. Oh, sorry. I don't want just y. Oh, I'm gonna have to move over a bit here. My horizontal asymptote is going to be the limit as x approaches infinity of that thing. There we go. And that's going to be, let's see, so that's going to be the limit. I don't want an equals in there. I don't know why I put an equals in there. Go away. There, that's what I wanted, a bracket. So I want the limit as x approaches infinity of 1 plus 1 over x, 1 minus 2 over x. And again, think about what that's going to be. That's just going to be 1. So therefore, y equals 1 is a horizontal asymptote. And for vertical asymptotes, x can't equal 2. So I want to consider the limit as x approaches 2 from the left, and I want to consider the limit as x approaches 2 from the right. And what's that going to be? How do I figure that out? Well, as you can see, that is just going to, there's no way I can kind of fix this so that I don't get 0 on the bottom. But as I approach 0, think about what's happening here, right? Am I approaching positive or negative infinity here? If I put in a number that's approaching 2 from the left, it's smaller than 2. So I'm going to get a very, very tiny, small, what kind of number? Small negative. And a positive, and then that's going to be, of course, that's going to be then a positive divided by a negative. So that's going to equal negative infinity. If I approach this from the positive, this is going to be a positive divided by a very small positive. So that's going to then approach positive infinity. Okay, my time's up for the people who got to run off to music. Later on this afternoon, I'll post the video for this, so we'll take a quick break for a minute here, and I'm just going to finish like 2 more examples, and that'll be part of your homework for the weekend, is to just watch the end of the video. When I post it, I'll even put on the blog what time you can pick it up at. Like 10 more minutes of video. That's about it. Okay? Have fun in music. Are you guys getting to drum now at least? You don't even get to drum anymore? You're learning how to conduct. Oh, congratulations. Oh. If this video that I'm going to post lasts on YouTube like years from now, nobody's going to know why the heck that mattered. What do you mean you don't even get to play instruments? Oh, the COVID era. Okay, I'm just going to finish off a couple more examples here, and then you guys who are on your prep can go. Find the horizontal and vertical asymptotes of this function. Okay, this one is definitely something like a driveway graph, because I definitely have 2 vertical asymptotes, right? Because there's 2 numbers here that x can't be. Can you see them? How do I know? Because there's 2 numbers that are going to make x 0, right? 3 and 2. So I kind of have to figure out what's happening. What's the limit as x approaches 3 from the left of this thing? So I'm going to actually leave it in factored form because it's actually easier to look at that way. Oops. And then I'm going to make a mistake. Yeah. There we go. So, okay, think about what happens to this thing. Well, if I approach 3 from the left, this thing's going to be positive. This thing's going to be positive. But 3 from the left is smaller than 3, so this thing's going to be negative. So I am approaching negative infinity, right? Now let's see what happens when I approach that limit from the right. Write the function down again. Okay, so if I put in a number a little bigger than 3, even if it's really tinily bigger, tinily? I think tinily might be a word, I don't know. Very close to 3, but just a very tiny bit bigger. Now this part's still positive. That's positive, that's positive. So overall, this function must be approaching positive infinity. And then, of course, we have to do the next. What about the other one? What about the limit as x approaches -2 from the left? Okay, so once again, just writing the function down. Okay, so as I go closer to -2, but I'm actually at -1.99999, this thing's negative, and this thing would be very slightly positive. So that ends up being a negative divided by a negative. So this guy's approaching positive infinity, right? And if I take the limit of this thing as I approach 2 from the right, this guy's still positive, this guy's definitely positive, and this guy now is positive. So I have a positive over a positive, which is still, that doesn't look like an equals, it looks like a greater than. Over here equals positive infinity. So notice the behavior at one asymptote is a little different than the behavior at the other, right? On one asymptote, the arms are definitely going, well, hang on a sec. Did I do this right? This is a positive over a positive over a positive, which is infinity. This one's a negative over a negative.
Last one, you left the 2 as a positive. Should be a negative, shouldn't it?
Where? Which one?
You copied it down wrong. In the last limit, you did 2.
Last limit I did?
X approaching 2 plus.
Oh, there we go. Yeah, thank you. That's the mistake. Thank you.
And then the x plus 3 should be a minus.
Right. There we go. Erase that. So this is going to be, as I approach 2 from the, yeah, I switched the signs for some bizarre reason. Thanks for being awake out there. All right, there we go. As I approach 2 from the positive, this is definitely going to be a positive over a negative times a positive, right? So that's definitely going to approach negative infinity. Okay, so there's, so these two guys, again, they're opposite directions, and that makes sense. And then, of course, what's this thing going to look like when we graph it? Oh, we're not done yet. That was the vertical. Let's do the horizontal. So the horizontal asymptote will be the limits as x approaches infinity of x over, I'm going to go back to the non-factored one because I have to use my technique where I divide top and bottom by x squared. And okay, what's going to happen this time? Well, I'm going to end up with 1 over x, and I can pretty much just stop there, really. I'll just continue just out of sense of duty. But there we go. What's the top going to be as x gets bigger and blows up? It's going to be 0. What about as x gets smaller, heads to negative infinity? Would it matter? No. So therefore, y equals 0 is my horizontal asymptote. But once again, that doesn't mean that y can't be 0. It just means as x goes shooting forever left and right, it goes to infinity. And I can show you that on my graph. Let's take that one away. And we are now doing this one. And as you can see, right? Notice again, the asymptotes are in opposite directions. One's shooting down forever, then the one right next to it's shooting up forever. But it does actually cross y equals 0. But as you go to infinity, you'll never touch it again. As you go to negative infinity, you'll never touch it again. Okay, I'm going to do one more example, then we'll wrap up this little video here. Okay, so one more. One more. Whoops. No! There we go. There we go. Okay, one more. I skipped example. This should be example 5. I decided to skip the one the book had. Sketch the graphs of y equals, sketch the graph of y equals x minus 3 squared, x plus 2 times 1 minus x by finding its intercepts and its limits as x approaches infinity and negative infinity. Okay, so this guy here, what we're going to do with this guy is, first of all, again, I want to sketch a graph, so I could first of all maybe find the y-intercept. The y-intercept happens when x is 0. So that'd be negative 3 squared times 2 times 1. So y is equal to 9 times 2 is 18, right? The x-intercepts, this is in factored form, so that's very nice. So the x-intercepts happen when y is 0. So that means that x is 3, x is negative 2, and x would be 1 are all of my x-intercepts. And does anybody remember what this is called? Because there's a little squared here. Begins with an M. And again, that's only for the people who have done the grade 12 course already. What do you call that on a factor? Begins with an M. Where's my guys who have done grade 12? That's a few of you still in the room. It's called a multiplicity. Remember that? Okay. So you should have kind of a good sense now of what this thing looks like. We'll sketch it in a minute. But let's talk about what happens when the limit when x approaches infinity. So as x approaches infinity, of course, I'm going, well, obviously this thing blows up to infinity, but think about it. It ends up being a positive squared times a positive, and 1 minus a really big number is always going to be negative. So it's a positive times a negative. It's going to head to negative infinity. What about the limit as x goes to the left forever? Well, now I get a negative in the first bracket, but I'm squaring it. I don't care how big the negative is, negative a billion, negative a trillion. Once I square it, what happens to it? It becomes positive again. So that's going to be negative squared times a negative times a positive, right? So that's actually a positive times a negative times a positive. So that's also heading to negative infinity. So that actually tells me something that maybe I didn't realize just looking at the function beforehand. Both of its end arms head down. So in the end, what do I know about this thing? If I wanted to sketch it, what do I know about this graph? Well, I know that it has a an x-intercept of negative 2. It has a y-intercept up here at 18. It has another x-intercept. I can't see my own work, so I have to look back at my notes here. It's at 1. And then the other one was 3. And I just found out that it doesn't have horizontal or vertical asymptotes, but I know that these arms are going to go down forever. And I know that this arm is going to go down forever. And I also know that, again, let's see, would this thing have a horizontal asymptote? No, it would not. So I know it's going to go up, down, and something like that, right? Oh, wait, I didn't draw that very good. Let me draw that again. I'm going to up, down, and then that's a multiplicity, right? So it just bumps into the line. Now, remember that. This should go much smoother than that. Let me just make that a little prettier before I small eraser. Small eraser. Something like that. There we go. Okay. Now, remember that right now I'm kind of not knowing how high and how low those are, but remember that's what we just did in our other lessons for this chapter. So we could put together that knowledge with this knowledge and have a very good sketch of the curve, and that's why they call this chapter curve sketching. So that's about as far as we need to talk about with asymptotes. So I'll end this little video. Thanks for watching. And I'll post it to YouTube for the guys who had to leave. Okay. And you guys who are working at home still, and you guys who are working in the class, if you have anything from 4 point whatever, the chapters before this that you're stuck on, we can help you right here. Let me just get this going. Okay, stop recording. Come on YouTube.